So let's see, for this one, I have a linear transformation from R square to R square. So it's from a plane to a plane. And it sends 1, 0, the standard basis, to 2, 3. And it sends 0, 1, the other standard basis, to negative 4 and 5. Now I'd like to find t of 1, 3. Well, I can actually see that 1, 3 is just 1, 0 plus 3 times 0, 1. So, if I want to find t of this guy, t of this guy is just going to be t of this guy. And because this is a linear transformation, t of 1, 0 plus 3 of 0, 1 is just going to be t of 1, 0 plus 3 times t of 0, 1. Yeah. Okay. So let me actually just write parentheses just for whatever reason. Now then, what is t of 1, 0? Well, we see from up here, t of 1, 0 is just 2, 3. And then 3, and then t of 0, 1. T of 0, 1 is just negative 4 and 5. So then this guy, I'm gonna have, let's see, negative 12 plus 2, so that's negative 10. I have 15 plus 3, so that's 18. So that's my t of 1, 3. Now for the next part, I would like to write t in the matrix form. We know t is a linear transformation, so actually there is a matrix where t of whatever is just going to be some matrix times that whatever. Now then, what is this matrix then? Well, we actually kind of see a hint of what this is in the example earlier. If we go back in the example 3.1, notice how when I look at t of 1, 0, okay, I run out of color to use, t of 1, 0, which is going to be 1, 2, 9, and that is the first column of my matrix here. Okay, maybe you can see here. And that is just the first column of my matrix here. Now then, t of the second basis, 0, 1, is 5, 1, 3. And that is my second column here, 5, 1, 3. This is actually true in general, and that's the second part of the second bullet here. The matrix form for a linear transformation is this guy. It's just where it is just, I just have to look at the standard basis, E1 to En. I look up where my E1 goes to, and I put that as the first column. I look up where my E2 goes to, and that is my second column. And so on. I look at where my last basis go to, and that is my last column. Okay. So let me apply this for my example down here. My matrix T, my matrix A, it's gonna be just, I look at where my first basis, notice that 1, 0, this is the first basis, 0, 1, this is the second basis. 1, 0, the first basis go to 2, 3, so my 2, 3 goes here. The second basis go to negative 4 and 5, so negative 4 and 5 goes here, okay. So this is the matrix form for the linear transformation that we have. Let's actually just double check real quick. If I multiply this matrix to the vector that we have in the example for the part A, this is 1, 3. That is gonna give me negative 10 and then 18. Negative 10 and 18. So indeed, this is the same number that we see before. Now, before I finish this example, let me actually show you what this all means geometrically. Okay, so let's look. I have this black matrix here. For now, my black matrix is the standard basis 1, 0. And I multiply this black matrix by the matrix that the black vector, with the matrix that we have earlier, 2, 3, negative 4, and 5. And I get this vector orange, which is 2, 3. So it is actually the 2, 3 that we see earlier. So that black matrix got sent to the orange matrix. Now let me move my black matrix around. you can kind of see my orange matrix kind of move along. So the image of my black matrix here is going to be my orange matrix. And if I move this to, let's see, 0, 1, I get negative 4, 5, which is the number that we see earlier. If I move my black matrix to negative 1, this is negative 2, negative 3, which is the negative of 2, 3 that we see earlier. Now let me actually trace this guy and see what we have. Okay. Okay, let me actually kind of draw a heart shape here. So you can kind of see my black, I have a black heart shape, and that black heart shape actually got sent to the bigger and rotated the orange heart shape down here, out there. So in a way, what linear transformation does is that it kind of sends one thing to another thing where the thing, they can be rotated, they can be bigger, and they can be skewed. So in a way, linear transformation has to do with what we have in image processing. So when we try to draw like a rectangle using standard program, you can make it small, you can make it big, you can make it small on one side, you can make it small on or bigger on the other side, you can you can scale it all together. You can kind of skew it like this. You turn a rectangle into a parallel pipe and you can rotate it. These things are what the linear transformation can do. You can scale picture, you can rotate picture, and then you can skew picture. Now then, let me actually, okay, let me kind of move, right, okay, let me leave this for now. Let me actually show you what this means when I have a picture. Okay, now then I have the same thing again. This black matrix got sent to the orange matrix. Now under the very same linear transformation, my smaller Google logo icon thing is going to be sent to this bigger Google logo icon thing. The green point got sent to the green point, so the origin stays the same. If you multiply a matrix by 0, 0, you get 0, 0. So the green point becomes the green point. The yellow point, the lower right corner, got sent to the lower right corner that you see here. The red point, the upper left corner, got sent to the red point, upper left corner. Now you can kind of see the, my black go to orange, so 1, 0 go to 2, 3, my red go to my red. What is this again? 0, 1 go to negative 4 and 5. And then 1, 1, it goes to the sum of the two, which is negative 2 and 8. So let me move this black and orange picture out of the way. So now if I move my blue point around, this is actually what this 2, 3, negative 4, 5 matrix thing did to my Google picture. This is what the linear transformation did to my Google picture. Now I can kind of flip this and it will flip my my picture as well. Now let me kind of move my red point around as well. So in a way, this is what the linear transformation does in terms of image processing. Okay, let me kind of reset this to the original position. Well, before I finish, let me actually just mention one thing real quick. My original Google icon. Now, if you notice, this guy has area 1 at the moment. If I make it twice as big, my image is going to be twice as big. If I make it half as big, my image is going to be half as big. So, now, when my, for the original Google icon, the area of this guy is 1. The area of the image of it is going to be 22, and that is actually the determinant of my matrix well, in this case, it's called M here. No matter how I draw my original picture, my transform picture is always going to be 22 times bigger than my original picture here. Right, okay. I should not have moved my green point, okay. Okay, so let me finish this for now.